So a couple of housekeeping before we start. So I think Arun already shared with you some of the lecture notes. So I'm using them as a guidelines, but I'll be talking more than what is there on lecture notes, right? Because I was too lazy to write down everything on the lecture notes. So I'm using that as more as a template rather than the actual lectures which I'm going to deliver. Okay. So the first couple of lectures in the lecture notes has to do with the SVD, the singular value decomposition, least square problem, the projection theorem, and I'm also talking about methods used for data dimension reduction, like when you're dealing with static data. My original plan was to sort of cover them very briefly in this, but then I realized that if I start doing that, then I don't think I will be able to devote the amount of time that I want to devote for the actual thing which I want to talk about. So that's why I'm just sort of leaving it up to you, but I'll be more than happy if you have questions on that to entertain those outside the right. So all I want you to sort of get familiar with is what is singular value decomposition, what is the projection theorem, how do you solve least square problems. These I feel are very basic things, but are actually kind of an underpinning for whatever the methods or whatever the approximation methods that we're going to talk about in a subsequent lecture. Okay, so even if you don't know them right now, maybe we can talk about them in the afternoon or sometime. So that's one thing. I'm also, during these lectures, I'm also going to provide you with a couple of codes, right? So maybe 3 to 4 codes. Those are all there in my GitHub repository. So I'll provide an access to those codes. That way you can actually, whatever you're learning here, you can always sort of go back and play with some simple examples and see how things looks like, right? Because you can always complement them with whatever the theory I'm doing in the class. So that way it's, you get to see like how exactly these things are working, right? So those things, and of course, I mean, if you are able to sort of develop it further, I mean, it will be good for me as well, right? So these codes are not something which is, I mean, there are some element of it which is sort of developed in our own lab, but there are some codes which are fairly standard. And these days with ChatGPT and all this AI platform, you can always go and ask for these kind of codes online. But I'll provide some context to whatever codes I'm providing. Okay, so that's another thing. The third thing is about the assignment. So if you are really interested, I'll be like, if you feel that you learn better with assignments, I can always give you assignments. Although I'm not a big fan of assignments, but if you want, it's all sort of up to you. It's all driven by you, right? So you can, if you are depending upon your initiative, we can actually take it even further. Okay, so that's so I think these are some of the housekeeping stuff. So I think any questions before we sort of dive into this? Okay, I hope my handwriting is eligible. I mean, sorry, you can actually, not eligible, you can actually read it, right? If I'll try to be as, with these days, I don't do a lot of writing, so everything on the LaTeX or everything on the computer, so it kind of affects your writing, but once in a while I have to write, and that's what it is. So I'll try to be very slow and make sure that it is readable, but yeah. So anyway, so let's start. Professor Arun has been talking about, like yesterday, he spent 2-3 lectures, and today again we're going to continue on this. And I sort of gave you a glimpse of what I'm going to talk about in yesterday's lecture. So let me just sort of reiterate and sort of re-emphasize a few things. So what Arun has been talking about is like a way of analyzing or looking at dynamical system, right? And that sort of viewpoint is developed almost 200 years ago in the work of Henry Poincaré, which is basically has to do with a geometric way of looking at things, right? So what what Arun talked about yesterday was how do you actually understand, or how do you actually model system in a state space and then how do you actually, once you have a model of a system in a state space, how do you actually analyze that model, right? So we like things like x dot equals f of x, you look at some initial condition, and then you want to see how the initial condition sort of evolves and gives you the trajectory, which so one of the notation we use is phi t of x, which is what does it mean is that you start at initial condition x and you want to look at the flow. So he introduced the terminology, want to look at the flow of the dynamical system, and the flow notation is phi t of x. So what does phi t of x means? It means that starting at some initial condition x, you want to know where the system will be at some time t, right? So that's sort of, so you can have a continuous time system, or you can also have a discrete time system, right? So something like xt plus 1 equals f of xt, right? So I don't know if you're familiar with discrete time system, but discrete time system are a little simpler to understand than a continuous time system. So what a discrete time system is, you have xt, which is the state of the system at time t, and then you want to know where the state will be at next time t plus 1, right? So you start with some x0, and then it goes to x1, and then it goes to x2, and so on and so forth, right? x3, and so on and so forth, right? So you can either have a continuous time dynamical system which leads to a flow, or you can have discrete time dynamical system which has an orbit. So as you can see, I'm sort of trying to motivate this without sort of going into any mathematical details, right? So I'm hoping that is okay, because I want to get the main idea out, okay, rather than sort of getting stuck in the mathematical notation. So assuming that all the regularity assumptions holds true for existence of solutions, some of which Arun already spoke about, I mean, this is what it is, right? So basically what is happening in this Poincaré's world is that you're looking at the system model from a state space point of view, where you have some initial condition in the state space, and you see how that initial condition is evolving over time, right? So that's fine. There's an alternate viewpoint. There's an alternate way of looking at reality. So, which is basically comes from the work of Koopman and von Neumann. These are two giants, Koopman and okay. So what are these? And if for those who have known about quantum mechanics, and this sort of ideas actually comes from there. I mean, you don't need to know quantum mechanics, neither do I. I don't know quantum mechanics, but I know what is the mathematical underpinning, or what tools that are used to understand quantum mechanics. So in this world, what you look at, instead of looking at evolution of point, you're looking at evolution of functions. Okay? So you have some function, let's say f0, and you want to know where the function will be at time 1. Like f1 is a new function at some later time. Just like in this case, you have x0 is initial condition, and then x0 goes to x1. Instead, now we say, okay, we have some initial function, and the initial function evolves to a new function. Now, this is already getting a little abstract. So what is, I mean, we have good understanding of what is mean by initial state is. Everybody sort of know what the state of the system is, and we know what the evolution of that state looks like. But what do you mean by evolution of the functions, right? So let's just look at a simple example. So think of a temperature in this room. Okay. So what is the temperature? So so this is a three-dimensional space, right? In three-dimensional space, temperature is a field. What do you mean by that? If you take any point in the three-dimensional space, you can associate a number to that point. What is a number? Number is a temperature at that point, right? So just to make things more easy to visualize, because let's take a slice in this three-dimensional space. So we have some plane, and I want to look at a temperature at different point in the plane, right? So that will be, if I want to visualize it from the point of view of visualization, I can visualize it as following. So I have x1, x2 as the plane, and then I have a function which is defined on this, right? And what is this function? Function is, let's say, it's basically a temperature, right? So it's a scalar value function, basically, right? It's a scalar value function because given any point x1, x2, I can associate a number which is the value of the function at that point. And you can ask, okay, this is a function, or this is a temperature in this slice at some time, let's say initial time t0. Okay, you want to know what will be the temperature at some time later time t1, right? How the temperature is evolving. So that's exactly how this function is evolving. So at some time t0, let's say the f0 is the function, right? f0 is my function. Okay. f0 is my function, and that will evolve to some new function at some later time. Agree? Something like this, right? So this is could be a simple example of how the function is evolving over time, right? And I still you may still not see this connection with the Poincare review. So let's just take look at one more example. Okay, so let's take an example of a fluid flow. I mean, I don't want you to sort of I'm not expecting from you to know what a fluid flow is, but let me just tell you very briefly. So what is I mean, if I'm looking at just a planar flow, let's say flow in a two-dimensional. So how is say if you put a particle in a flow, right, the particle will evolve, right? So why is the particle evolving? Because there is a fluid flow will have an underlying vector field, like just like what Arun talked about yesterday. So let's say if I have a two-dimensional flow, that means in a plane, x1, x2 plane, right? In the x1, x2 plane, I have a flow field. That means at every point I can associate a velocity, right? So this is a vector field. So this is a x dot equal f of x kind of a vector field. Now, if you put a particle here, then the particle will evolve just like in the Poincare's viewpoint. So if you put a particle in this flow field, it will evolve and do its own thing, whatever, right? Depending upon the vector field, right? But instead of looking at how the particle is evolving, I can ask, okay, what if I actually put a dye, some color dye in this fluid, right? So what is the color dye? So if I want to actually visualize it, so again I have this two-dimensional plane, x1, x2, right? There is an underlying flow field. I'm not going to draw it, just you imagine that there is an underlying flow field, but I put some color dye, let's say a red color dye. So what is the red color dye? Red color dye will be something like this, right? So it will be red, you put a small ink drop, a red ink drop, and then you can ask, okay, what will be the fate of this dye, right? Now, if you want to describe the evolution of this fate of the dye, how will you describe it? So if you think about it, how do you describe this? So I can say, oh, at time t equal to 0, I put a dye here, right? So how do you describe it? I say, oh, at time t equal to 0, there is a function f0 of x, which is 1. So let's say this is a set, right? So let's say this is a set A, right? So I can describe this initial location of dye by saying that at time t equal to 0, there is a function f0 of x, which is 1 for all x belongs to A, and is 0 for x does not belongs to A, right? Now again I have a function. You see what I'm saying? So now I can ask, okay, at some later time this dye will deform and look like this, right? So this function will now, this was my f0 function, this f0 has evolved to some f1 of x. So now I'm interested in knowing how this has evolved to f1 of x. What is this evolution, right? What is this evolution f1 of x? How can I describe the connection between f0, which is my initial location of dye, and the location of dye at some later time f1 of x? Does that make sense? Right? And how these are evolving? These are evolving because there is an underlying vector field in this flow. So the underlying vector field is still the same, right? So it is still the same, which is coming from something like x dot equal f of x, right? So only difference is that instead of looking at an evolution of a single point, which is what you do in the Poincare's world, now we are looking at an evolution of not one point, but an ensemble of points, right? And an ensemble of points in the limit of large points, it becomes a function. Make sense? So basically this Koopman-von Neumann world, we are not looking at evolution of a single point, because evolution of single point have no meaning in the Koopman-von Neumann world. What you can describe is actually evolution of an ensemble of points, which is easy to describe in terms of a functions. Or put it simply, we are looking at how the sets are evolving. Okay? How a set is evolving, and how you describe a set. You can describe a set using function. Okay? So I hope this sort of actually tells you the difference between these two different viewpoints, right? And one thing to sort of understand, one thing to sort of realize is that both this Poincaré world and this von Neumann world are trying to describe a reality, okay? But they are not reality, right? So when we often actually sort of make a mistake of considering model as a reality, right? So when I say, oh, I have a nonlinear model, right, of a system is not nonlinear or linear, right? It is just the way you're describing the system, right? So the system can never be linear or nonlinear. I mean, it's just the way you're modeling it, right? In some other world, maybe there is no nonlinear, right? So both this Poincaré's way of describing, or I mean, not I would say Poincaré, but what I'm like making a little even more bigger statement is that whatever model you have, like the model which you are sort of familiar with, which is the differential equation way of modeling things based on calculus or even discrete time systems, these are just a way of describing a phenomena, okay? Way of describing a phenomena. The phenomena could be linear, nonlinear, but the way you describe it, it's all up to you. I could describe what is happening outside using a linear model or a nonlinear model, right? It is not, it is nothing, it says nothing about the reality. I mean, whatever the reality is, I mean, if you feel that there is a reality, right? So, although you use this idea of linear, nonlinear model, but really we should be talking about not a linear, nonlinear model, but we should talk about linear, nonlinear phenomena. Okay, so there is a phenomena which is out there which we can describe using linear, nonlinear model. Okay, what I was like coming back to this Poincaré von Neumann way of describing things is that both these ways are actually are trying to describe a phenomena or a system. So these are just a model, okay? And then one model may be better suited for one thing, other model may be better suited for some other thing, right? So I mean, you cannot have one single model which describes everything, right? I mean, we know from statistical mechanics, I mean, if I want to describe a temperature in this room, I mean, that's like, I mean, I have to deal with so many atoms, right? So I have to describe that using, like, I need to know interaction at the atomic level to come up with the temperature. But we have a very simple way of describing temperature using statistical mechanics. And that serves the purpose, right? And so model is as good as what you want to do with the model, okay? So sometimes reduced order models, so let's say, for example, if you want to do a control, having a very crude model is good enough. Right? You don't need to describe things in a gory detail, because if you try to describe things in gory detail, that model is useless for control. Okay? On the other hand, in some cases, we need to know things to a gory detail to look at, like, for example, prediction problems. And that's why it's so difficult to actually tell what will be like a weather like tomorrow, because these models to describe the weather are actually highly complex models, which are like a Navier-Stokes equation, and these have all sorts of complex behavior. But there is no other alternative. So if I want to know what will be the temperature tomorrow, is it going to rain or not rain, I have to deal with those very detailed models. Okay, otherwise I will miss the physics, and I will have there will be huge uncertainty and things like that. Right. So models are as good as what you want to do with the model. Okay, and then they are trying to describe the reality. So that's about the model. Now, the claim is, and it's something that will be tested by time. The claim is that when it comes to now dealing with the kind of problems that we're dealing with these days, by that I mean that we're dealing with systems which are man-made engineering systems. These are highly complex systems. The physics-based models are not that useful. And there are a couple of things here, right? Let me just open that thing up. So, like, make things more concrete. Let's say I'm trying to design some vehicle, right, which can navigate autonomously on some rough terrain, right? Now, if you think about that problem has like multi-physics, right? Because the vehicle dynamics, there's a physics there which we understand very well. So you can write down Euler-Lagrange kind of equations to model the vehicles, right? But now when you actually try to understand the interaction of the vehicles with the terrain, those terrains are actually could be like, if you have a sand, then those are actually described by PDEs, right? If it is navigating in the water, then you have a fluid mechanics. I mean, so the point I'm trying to make is that now we are dealing with kind of systems which have multiple physics, and these physics sometimes may not be even able to capture using first principles. Okay, so that's one thing. The other thing is that on other side we have now, because of this advancements in sensor technologies or advancement in computation, we have lots of data, right? Now, why can't we use that data to actually resolve this problem, right? Which is, can we actually come up with a model rather than relying on first principle approach? Can we actually use data, because data is actually cannot lie, right? So data is what it is. Can we use those data to actually build models and then do whatever we want to do with those models, either do prediction problems or controls problems? So claim we want to make is that, or I'm making is that, this Koopman von Neumann way of looking at things is actually better suited when it comes to looking at some of these complex systems where we are dealing with multi-physics, complex physics, and but at the same time we have a lot of data, right? So we can think of this. I'm going to talk about this. We can think of this linear operator as a model themselves, right? So we can actually take data and use those data to construct model, and that could be very well be the model of the system, right? So we don't have to think about model as something which is described using differential equations, right? So that serves some purpose, but at some point it just fails, right? I mean, if you think about all the chat GPT and all those things, I mean, those are not based on differential equations. They're all like neural networks and things, right? So, I mean, although it's a dynamical system, if you think about it, there is a dynamical system there, but you cannot really describe, and that's actually been an open problem, is like, is there a simple laws that you can actually design to understand those complex systems? So we're building complex systems, and is there a way to actually understand how to analyze the system so we can design them better? Okay? So the claim I'm making is that this Koopman von Neumann way of looking at things is very well suited in this modern era where the data is plenty and we are dealing with systems which are highly complex. Okay? And hopefully that's you can see that as we progress. Okay? Any questions? I mean, I'm throwing a lot of words here, but I think those are very important because I think many of you may not have seen systems from this lenses. Okay? So any questions? Like you'll have to sort of make it more like refine that question, right? Okay, what do you mean by lower limits and things like that? Okay. Yeah, so I mean that's again will depend upon like what applications you're dealing with, right? So I think what kind of phenomena you're trying to describe, right? So if you're trying to describe phenomena which is changing very rapidly, and of course you'll expect that you'll need more data. So whereas if you're dealing with something which is not really changing much, I mean, less data is useful. And now what do you mean by, you can ask, okay, what do you mean by not changing much? What do you mean by changing a lot, right? So can you quantify it? And certainly we can quantify them, but all sort of depend upon like a very specific application. Unless sort of we work with a specific application, it will be difficult to answer that in like a very generality. And some of these things are actually people are still trying to understand, right? It's not like everything is solved. And I think some of this, especially from the practical implementation point of view, there is also some trial and error stuff there, right? So you try certain things, as I said, you will never have, I mean, more the merrier, data more the merrier, but I mean, you always know that if you have more data and you're trying to fit certain things, you have this classic problem of overfitting, right? So you can do a very good job of yeah, you can do a very good job with regard to explaining the data with the model. But when it comes to explaining something which the model is not seen, you may have some problem. So there are all this sort of issues comes in, and these problems are not like far from being solved, right? In generality. So yeah. Any other question? Good. Yes, I mean that's perfectly valid, and I think I will tell you. I mean, some of these things again. I mean, they're a sort of active area of research, and I can tell you my viewpoint with a specific example as well. Like so how we can actually combine classical models with the neural network kind of model, which where the neural network sort of can help you sort of understand the part of the physics which cannot be written down using Newton's equation. So there are ways of actually doing it, and yeah, certainly. Yes. So those are all sort of things one could explore. Yeah. Any other question? No. Okay. So while this is sort of good at a particular high level, let me now try to go a little more detail with a simple example to get this point, like further reinforce this point. Okay, why this functional approach is better than the point-wise approach. So that's the point I want to make it again with a simple example. Okay? So I don't know how many of you are sort of familiar with the logistic map. Have you guys heard of what is called logistic map? No? Okay, so you don't, let me, if you just like Google logistic map, you will see all sorts of things, but let me just tell you very briefly without sort of diverting from it. So what is the logistic map? So I think, as I said, I think the discrete times is actually, systems are actually much easier to sort of understand. So I will start with a simple, it cannot get any simpler than this. There's a simple one-dimensional discrete time system, okay? One-dimensional discrete time system. And this discrete time system is described using following equation. So you have xt plus 1 equals alpha xt 1 minus xt, okay? So what it is saying is that, and alpha is some parameter. So, so this is called as a logistic map. And this is like one of the highly studied maps when you want to actually look at all sorts of complex behavior a nonlinear system can exhibit, right? So some of the things which Arun talked about yesterday was, okay, you have a nonlinear system, you can look at linearization of a nonlinear system, you get a fixed point, and there could be other phenomena that you can have in a nonlinear system like a periodic orbit or limit cycles and things like that. Now, think of all those phenomena on drugs, okay? So this system, since I don't want to spend a lot of time, I'm just going to like give a very, paint a very broad stroke. So the point is really not to actually kind of tell you how complex the system, I mean, how complex the behavior is. The point actually is that while the system behaves very complex in the state space, the description of the system when I look in a function space is perfectly fine. Okay? So what is this system is, right? So what is the system? This system first of all actually evolves on 0, 1. Okay? So your x here belongs to 0, 1. Now, what happens with the system is alpha is a parameter. Okay? So as you change alpha, the system behavior changes. So for what happens is that for some value of alpha, the system will have only one stable equilibrium point. Okay? Now you increase the value of alpha. At some point, the one stable equilibrium point becomes two stable equilibrium point. Okay? And then the stable one becomes unstable, and then a two stable equilibrium point emerges. And then you increase the value of alpha a little bit more, 2 becomes 4, 4 becomes 8. So it grows like 2 to the power n. So with the alpha changing between 1 and 4, you sort of get all sort of complex behavior. The system will have like infinitely many fixed points. System will have, and then at a particular value of parameter, I don't know precisely because as I said, the point is not to dive deeper in this. At some point of the value of alpha, the system gets a periodic orbit. There's a period 3, and then a period 3 implies chaos. So this system has all sorts of complex behavior that one could imagine the nonlinear system can exhibit. It will have a periodic orbit of arbitrarily large period. Okay? it will have fixed points, as many fixed points that you want. It will have what is called as a dense orbit. Okay, what is a dense orbit? Is that there is an orbit in the system. By orbit, I mean, I already told you orbit, but just to tell you again, what is orbit? So you take an initial condition and you look at where the initial condition goes next time. So you have x0. So this is basically you take x0, then it goes to x1, this goes to x2, and then x3, and so on, right? So this is what is called as a dense orbit. So what is a dense orbit? Means that pick any number between 0 and 1 of your choice, and there will be an orbit which comes and pick a number between 0 and 1 and pick an epsilon, howsoever small the epsilon is. There is an orbit which will come within epsilon distance of that point. Okay, so that will be, that orbit is called a dense orbit. So there will be a dense orbit. This system also has what is called chaotic behavior, which means that this system has a so-called sensitive dependence on initial condition. So if you take any two initial condition, by the way, this everything happens between 0, 1. Okay, you don't have to go to infinity. So everything happens between 0, 1. So you take any two initial condition and look at how this two initial condition evolves forward in time. They will diverge exponentially. So that's basically the signature of what is called a chaotic behavior. So if you look at a typical trajectory of the system, this typical trajectory of the system will look like a walk. It will look like random. It won't make any sense. Okay, any typical trajectory, because especially for alpha equal to 4, where you see all these things. So if you look at a typical trajectory of the system, if this is my n and this is my x, I will see something like this. Okay, I mean, I'm just doing it continuous. These are all discrete. These are discrete points. I'm just joining those discrete points, and it look completely random. Okay, it won't make sense of it. Now I can ask, okay, this is how the picture looks like in the Poincaré's world. How does the picture looks like in the Koopman-von Neumann's world? Now, how do you describe that? You say that just like we said in von Neumann's world, we are not looking at evolution of point. Okay, we are looking at evolution of functions. So what does it mean? Okay, I will take some function. So for simplicity, I could take some function, let's say a uniform function. So I have some uniform function. So this is my x-axis. This is my function f0 of x. So what it means is that, I mean, this function is just 1 between 0, 1, right? So this is my initial function, okay? And I want to know how this function will evolve forward in time. Now, I understand, I mean, I still haven't told you how this functions evolve. We don't understand, I mean, we still don't know how the function evolve because I haven't told you what's the law which has been evolved. But we know how the points evolve, right? So how I describe the function using point? So the way to describe the function using point is say that, as I said, evolution of function, alternatively you can think of, instead of evolving one point, you are evolving ensembles of points, right? So you take a, so think, if you want to, very practically, what you do is that you form a grid. Like you partition the X space into some n intervals, capital N intervals, like 1, 2, dot, 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 to some capital N, okay? And you take uniform distribution of, let's say, like 1,000 points in this n intervals, okay? And uniformly spread, right? So that's what this F0 function means, right? This is a flat function, which is like a uniform distribution, okay? So you take all this 1,000 points, for example, and spread them uniformly in this n boxes. So these are n boxes, right? So they're like small, tiny intervals. And now you propagate this point, all this 1,000 point, one step forward. Okay? So that now you look at the distribution of these points one step. Now, how do you look at distribution of point? I'll tell you. Now, the function which describes the distribution of point one step, that will be the evolution of from F0 to F1. So, what do you mean by? So, let's say I have capital M points. M points uniformly distributed between 0, 1. Okay. Now, what you basically do is that you do a what is called a counting measure. Okay, so what I want to do is that, so if you think about, so this is my f0 function, which is constant function. I want to describe a new function f1 of x, which is how evolution of f0 in one time step under this system. Okay, I know how points evolve, so I want to tell you how this f0 will look like in one time step to evolve to f1. Okay, so the way I'll describe this function, so that I have n boxes, so instead of actually telling you the continuous discretional function, what I'm going to do is actually I'm just going to tell you what is the function value will be, and in each of these boxes. So this function will basically like a step function. Okay, now, so there are n boxes, so I need to tell you what is the value of this function in the n boxes. Okay, so the function is basically, think of this new function has been discretized. Okay, now if I pick, let's say some box, so this is my 1, 2, and so on till n, right? So let's say I pick this kth box. Okay, so I want to tell you what is the function value f1 in the kth boxes, right? So what is the value of this function in the kth box? Okay, so that's what I want to tell you. Okay, so how do you describe this value of the function in the kth box? So f1 k, okay, f1 k, it's just a number. It will be a counting measure. What it means is that I will pick the kth box. So I have total of m points. So I have a total of m points. So I will do 1 over m, and I will take the kth box. So let me call this interval as delta k. I'll denote this interval at delta k. Delta k times x1, or from x. Okay, so let me just introduce some notation. So I have m points. So let's just number these m points at time 0 as x0, 1 to x0 m, right? So these are my m points which are uniformly distributed. So the 0 here stands for the initial condition. 1 to m stands for the number of points. I have m points at time 0, and these points will go through this map. Let's call this map as s of xt. Okay, so I'm calling this as s of xt. S is a notation for the logistic map. So this m points will evolve x0k, right? So I take k, where k is going from 1 to m. This will evolve and gives me x1k. Right? 1 stands for one time step. Make sense? And k here is going from 1 to m for the m points. Okay, make sense? Easy, right? So I want to find, so maybe I'm sort of confusing notation. So instead of calling this k, let me use some other notation, because I'm using the k here. So let me use some other notation here. So let me call this, instead of calling this k, let me call this, you have some pet index that you like. Let me call this L. Okay. N are the number of intervals, m are the number of points. N are the total number. So this L is the index. So L goes from 1 to m, 1 to n, and k goes from 1 to m. Okay. So L is here will go from 1 to n because there are n boxes and there are m points, right? So this delta L, so 1 delta L will be x k equals 1 to m x1k. Sorry, I think this is x1k. Make sense? So what we are doing is, what is 1 delta L? 1 delta L is what called as the indicator function, or is also counting measure. So what you do is that whenever the x1, the next time step point, comes in the box delta L, I count as 1. If it doesn't come in the box delta L, I count as 0, right? And then I just do the, because there are m points, I just average it, right? It's 1 over m, okay? Make sense? So you have sort of m points uniformly distributed between 0, 1. You propagate these m points and count how many of these points land up in the delta L box and average them. So whatever number you get, you associate that number to this F1L. Okay. So that's the value of the function at the box, Lth box, F1L. Good. And this L will go from 1 to n. So that's how you get number for each of the n boxes. Good. Sorry, come again. Initial, all the points are uniformly distributed, and then they in the n boxes. Yes, all the m points are uniformly distributed in n boxes. I mean, you can take m to be n, but you can m could be m is larger than n. Okay? And then you want to know, and that's I'm assuming uniform distribution because f0 I'm assuming to be a flat function. If you take f0 to be some Gaussian, then you distribute this point based on Gaussian distribution. So where it will be larger point, where there is the peak of the Gaussian, and there is the right. So that's the idea. Does it make sense? Good. So far so good. Right. So this is essential. So that's how you get this. So I'm sort of, now you can take the limit, right? That's the power of the limit. Now you take delta as small as possible. Now this function will become a continuous function. I mean, sort of will become a continuous, right? So I'm sort of doing a discrete version of this. And those who have done some function analysis courses, you know that like all functions, you can always write them as a linear combination of the indicator function. So this is basically the idea, right? When you're binning this x-axis into these boxes, you're basically constructing a basis based on the indicator functions, right? So any function, you can write them as a sort of linear combination of the indicator function. Okay. Anyway, so you see where this is going, right? You see where this is going. So this is one time step. You can now repeat this second time step, third time step, fourth time step, and so on and so forth. And then you can ask, okay, how is this eventually, this function will look like? If I start with uniform distribution of function, in this case, the f0 is just happens to be one function, which is the uniform distribution. You can take any other function as initial distribution. Just like in a state space, in the Poincare world, you can take any initial condition and ask, okay, what's the fate of that initial condition will be as t goes to infinity. If the system is globally asymptotically stable, everything will go to the equilibrium point, right? If the system is globally asymptotically stable. Same question you can ask here. If I start with any possible distribution of initial condition, not just a uniform distribution of initial condition, what will be the eventual fate of that distribution will be? Okay. Now, for the logistic map, it turns out that although the pointwise behavior is very complex, as I said, it has system is chaotic, in fact, for alpha equal to 4. But in the space of functions, no matter what function you start with, this system is always going to converge to one single function. This system has like in the point, like speaking in terms of Poincare's world, because that's something you're familiar with. Just like we say, any initial condition will converge to one single equilibrium point. There is one single invariant function to which all functions, no matter what initial function is, will converge. So while the behavior of the system is very complex in the state space, it is highly regular. I mean, you cannot ask for anything more than that, because it's like no matter, it has like a unique attractor. The system has a unique attractor. Every function will converge to a single function. And I'll just and you can actually code this up. This may not be like a more than 5 to 10 line of code for this example, and you will be surprised to see that within few iterates, no matter what initial function you pick, it will always converge to a function which looks something like this. I'm drawing this in a continuous limit. Okay, I'm drawing this in a continuous limit. Okay, so this is my 0, 1, and this is my f star of x. The f star of x is like your steady state distribution. Okay. So things which could be like when you look at the pointwise evolution, it looks highly complex, it's highly nonlinear, it's even in fact chaotic. You cannot like ask for any more complex than that. But if you look at the same system and look at the evolution of the system in the function space, it is very well behaved. Okay. So this sort of tells you that there is an and right. I mean, I think the natural question will arise is that, okay, why may I want to look at evolution of functions, right? I'm happy with looking at evolution of points. Why do you want to look at evolution of functions? You could ask. I would like the argument could be, of course, you may want to buy it or not, is that in reality, if you think about reality, you will never know an exact initial condition of a system, right? You will never know exact initial condition. What you will know is that you know initial condition with some uncertainty, right? So there is an initial condition and then there is some uncertainty around it. So if you want to think in terms of Gaussian world, you say that, oh, the nominal initial condition, I mean, whatever initial condition you know is like a nominal initial condition, and then there is some small distribution around that, like a Gaussian distribution, for example, right? So there is the initial condition always comes with uncertainty. And if you think about the uncertainty is basically a function, right? Uncertainty is basically a function. So rather than actually looking, it makes much more sense to look at evolution of functions rather than evolution of a point, because that's what you can actually measure. You can never measure the single point, right? Because you always have some uncertainty in measurements. In real world, you always have uncertainty in measurements. And that's exactly this. All this motivation is coming from von Neumann's Koopman, because this all has to do with the quantum mechanics, right? In quantum mechanics, you can never describe the position and velocity exactly. That's why you're dealing with distribution, and this is exactly what we are doing here, right? So the fact that so in the system, so you see this system, there is no uncertainty in the system. This system is deterministic. There is no noise in the system. But you're still using methods which are actually developed for looking at evolution of distribution, which comes when you have noise, but although there is no noise. So the uncertainty is not coming from the noise, but the uncertainty is coming from the fact that you don't know exactly what the initial condition of the system is. Does that make sense? So you are using kind of statistical method to describe deterministic system. Not that a system is stochastic, not that a system has uncertainty, but you are still using the statistical methods, because I'm saying statistical methods because I'm looking at not one point, but I'm looking at evolution of ensembles of points. I'm looking at evolution of function, which is very natural when you're describing a system with uncertainty. Okay, we can still use those methods for looking at deterministic system because of the fact that although there is no noise in the system, there is an uncertainty in the initial condition. There is a lack of knowledge that you have about the initial condition, and that's why we are using this approach. Make sense? Yes. Good. So we'll get a Fokker-Planck will be is like a stochastic version of this. So when you have a noise, then this becomes exactly the Fokker-Planck in the continuous time and so on. So I'll talk about that. So you don't need to go. So the nice thing is that you don't need to go to the Fokker-Planck to talk about the evolution of functions, the probability density function, for example. Okay. Anyway, so I haven't really started with what the linear operators are. So this is where so I hope I have sort of given you enough motivation and not just motivation, but also the reason why this alternate viewpoint is actually advantageous. Okay, of course, some of this thing you have taken my words for it, but as I said, you can just go to the MATLAB and just go to ChatGPT and ask it to write a code for the evolution of this functions for the logistic map and see for yourself. Okay, it'll generate distributions like this. Okay? So it's very easy to verify. Okay? So if you buy whatever I'm saying so far, then I can now jump to little more abstraction. Okay, any questions? Yes. How can I what? Okay. Mm-hmm. Good question. So I think although I told you all those things, I'm going to like one big statement I'm going to make, which will actually like, I mean, some of you may know it, but most of you may not, and that will actually be an eye opener. And then I think it'll sort of precisely answer the question. So let me tell you now. So now you can ask the next question is that, okay, you tell me that there is an advantage in looking at evolution of functions rather than looking at evolution of points. Tell me how the evolution of function looks like, or rather, what is the underlying principle or underlying evolution for the evolution of function. So when it comes to evolution of point, I know the evolution of point is nonlinear, right? It's nonlinear in a state space. It turns out that evolution of function is actually linear. So even though your system is nonlinear, evolution of function is always linear. Now, if I give you two problems, one is a linear problem, one is a nonlinear problem, and ask you to pick one, what will you pick? Huh? Linear, right? That's what this evolution of functions is. Evolution of function is always linear. Whereas the evolution of point, although the evolution of point is nonlinear, evolution of function is always linear. And that's the big advantage. Okay, you'll say, okay, what is the catch? I mean, if the single point is evolving non-linearly, how can the ensemble of points actually evolve linearly? The ensemble of points in the limit, which is described using function, is evolving linearly. How come that is possible? What's the catch? Yes. So what I'm saying is that what is the catch? Like you're getting like converting nonlinear to linear. There has to be some catch, right? I mean, nothing comes for free in this world. So the catch is that although it is linear in a very high dimensional space. It's linear in an infinite dimensional space. Okay? It is linear in an infinite dimensional space because you're looking at function evolution. And functions are objects in infinite dimensional space. Okay? So you are converting nonlinear problem to a linear problem. That's a good thing. But the trade-off is that we are going from a finite dimensional nonlinear to infinite dimensional linear. So for example, in this logistic map, is a one-dimensional system. One-dimensional nonlinear system. This one-dimensional nonlinear system becomes a infinite dimensional linear system. This one-dimensional nonlinear system will become an infinite dimensional linear system. Okay? Of course, now what does infinite dimensional means and so on and so forth. So kind of tell you the long story short is that the way you now deal with the infinite dimensionality is sort of you use data to construct a finite dimensional model and then use this finite dimensional model as a surrogate, as an approximation for the infinite dimensional linear model. But linearity is what is actually paramount here. Because what does linearity does? Like based on what Arun taught you yesterday, the linear versus non-linear, what does linearity does? Why linear is so good and why non-linear is so bad? If you think non-linear is bad. Yeah, and I think we have very good intuition about linearity, right? Superposition, homogeneity. We know how linear things behaves, right? Nonlinear, we don't know. All our intuition fails. linear things, we have systematic ways of actually design methods, right? LQR, MPC, name it. Kalman filter, all these are actually not just, these are actually technologies now, right? These are no longer research. These are actually technologies. People are actually using them in everyday life, right? I mean, you launch satellites based on Kalman filters, right? So these are all technologies. Now, all these things are now comes to your disposal when you actually think like this. When you actually think about nonlinear system through this Koopman-Neumann's viewpoint, right? So we have very good intuition. We have mature tools for analyzing and designing of linear system. All those things can now be used to look at nonlinear systems. Okay? Of course, the devils are in the details. As I said, this is infinite dimensional nonlinear. I mean, infinite dimensional nonlinear is things could go wrong and infinite dimensional. I mean, we have intuition. Let me just correct it. We have good intuition for finite dimensional linear. We still don't have good intuition for infinite dimensional linear, but we can still make progress. Okay, we can still make some good progress, and I think linearization has got us so far, right? I mean, we did. Arun talked about linearization-based methods. We can design controllers based on linearization, and that works pretty well, right? Can we go one step further and deal with a nonlinear system, not through this lenses of linearization, but through the lens of this, I will call it as Koopman linearization, right? So which is not sort of a pointwise linearization, but through Koopman linearization. And furthermore, going forward, I also tell you sort of how do you actually go back from this function space to the state space, okay? Okay. So with that, let me now give you some, bore you with some definitions, okay? Because those are essentials, okay? So keep this, whatever I've done in mind, because I haven't done anything mathematical here, but I'm going to revisit this and pin down the mathematical equations which are used to describe these evolutions of functions and so on. Okay. Let me now start with a few definitions. So there are two ways of describing evolution of this function. Okay, and these two ways are actually a dual ways. Okay, so I'll tell you what a dual means here precisely mathematically. So the one way of describing it, so these two ways are described using two operators. These are linear operators. As I said, evolution of function is linear, so these two operators are linear. So you use this operator because you are now working on the space of functions. Okay, so this is, and these two operators called as a Koopman and Perron-Frobenius operators. Okay, so I will first talk about what the Koopman operator is, and I will talk about first in the context of a discrete time system, and then I will tell you how this two operator looks like in the continuous time case and so on. Okay, so let's just use some notation. So I will use the notation xt plus 1 equals f of xt. This is my discrete time system. So f is some mapping from S space X to space X. I'm not going into like all you need to describe this is actually that f has to be continuous. Okay, so all we need that the f is continuous, and we can also put some more structure on the underlying space X, but from you don't. Okay, so as I said, what is a discrete time system? Discrete time system is easy. You have initial state xt, and the f tells you where the next state xt plus 1 will be. Okay, it's basically a law, right? Now this f could be invertible or f may not be invertible, right? So what is invertible means that f has a unique inverse, right? So it may not be, like for example, in the logistic map case, this is not invertible. Okay, that means there are multiple points that will lead to the same point. Okay, so if you try to take the inverse, you will not get a one point, but you could get a multiple points. Okay, so this f, and I'll tell you places where I'll use the invertibility and where I will not use the invertibility, and so on. Because the what I'm going to talk about doesn't need invertible, but if it is invertible, then it has little more structure. So if you put more structure, then you get more structure. Okay, but anyway, so those are not important. Okay, so the first operator that we're going to talk about is called a Koopman operator. So it's called the Koopman operator. So let's just fix the notation. I want to see if I want to make sure that I'm consistent with the notations, but if I'm not, you can correct me. I want to make sure that I'm consistent with the notation which I have used in my lecture notes, so that because we're going to use a lot of them. Okay, we're going to use a lot of them. I think the notation I'm using in the lecture notes is, I think, is the calligraphic kappa. I think different textbooks. One other thing I would do is actually I will sort of tell you some of the references where I'm getting this from, because these are sort of very basic things. Okay, I'm actually also using a different notation for this system. I'm using, instead of F, I'm using the T. So let me just stick to that. That way we could, when you refer to this and the notes, you are not confused. Okay. So now what is the Koopman operator? So the Koopman operator is denoted by this kappa. So kappa is actually taking mapping functions to functions. So I'll use the notation cal f for a function space to cal f. So here again, I'm sort of very pedantic about what these function spaces are. So I mean, if I want to go a little more, do this more rigorously, then I have to put some structure. Like I have to define a measure on the underlying space, and I'll talk about is it L2 space and so on, and L1 space, what kind of. So I'm not doing that right now, because I think that you just because I want to get the main idea across, and then when it comes to sort of word of caution, I'll tell you that okay, now you have to be careful in what sort of function spaces you have to deal with. Okay, but that point hasn't reached yet. Okay, so this kappa is taking a functions and gives you a new function. So it maps a function and one function to another function. Just like T is taking you from a state space X to this to the space X is mapping from one space to another space. X here is the underlying state space. It's a finite dimensional state space. If we are working with Euclidean spaces, this will be a vector space. It could be a manifold as well, but it's just a space. It's a finite dimensional space, but a function space is a infinite dimensional space. Okay, and hence this kappa is a infinite dimensional operator. So now, how do you define this? So let's say I have a little f function which belongs to this f. So I have some function. Okay, now this kappa will act on this function. Okay, it takes kappa acts on a function. So for those who haven't seen this notation, that's why I'm a little slow here. So it takes kappa acts on a function f and gives me a new function. The value of the function at x, so that's the notation, right? So kappa takes a function, kappa f is a new function, and the value of the function at x is given by, you take the old function f and make it act on t of x. Make sense? So the value of the new function at point x is same as the old function evaluated at t of x. Okay, this is also called as a composition function, because you see this is basically f composed with t of x. Make sense? It's very easy to like write it down, right? But this actually, okay, when it comes to the Perron-Frobenius, I will make that comment. But it's very easy, right? I mean, it's describing this function is very easy. Okay. Now it's also very easy to see that this is a linear operator. What does it mean? That if I take kappa and make it act on a function which is alpha f1 plus some f2 of x, it is same as alpha f1 of x plus kappa f2 of x, right? right? Why is this? Because what is this? Is nothing but, using this definition, it will be alpha f1 plus f2 acting on t of x, right? Which is same as alpha f1 acting on t of x plus f2 acting on t of x, right? Which is same as alpha, what is f1 t of x, is nothing but kappa, so f1 of x by definition plus, right? So it's linear. Okay, it's a linear. Okay. So this f is also called as the observable. So as I was saying, like the first example I gave was like a temperature, right? So temperature is like observable. So you are taking some measurements. So you have a system, and you're taking some measurements from the system, and those measurements are a scalar valued measurement. So those measurements are like the f. So imagine that in this room, like the underlying flow field is the Navier-Stokes, but then you're taking measurements, like you're putting some sensors, you're putting distributed sensors to measure the temperature, right? And then so that's your the f function. Now you want to know what those measurements look like after some time. So kappa acts on the function and gives you new function, which is your new observables. So they are also referred to as observables. Okay. Now this Koopman is an infinite dimensional operator because it's acting on a space of functions. Okay. Any questions? Now it's going to get little uncomfortable, but let's see if you can dive a little slowly. So whenever you have a linear so this is a linear operator, right? So this is a I mean, if you've done a linear algebra course, right? So if you've done a linear algebra course, you know that you can always realize a linear operator, right? So linear operator is an abstract thing, but if you want to realize this thing, what you do is that you put some basis functions, and then you see the linear operator as a matrix, right? So it's just the arrays of numbers, right? So whenever you have a linear matrix, what's the first thing comes to your mind? What do you want to do with the linear matrix once you see a linear matrix? Diagonalize. Even before that, what are the sort of fundamental things of a linear matrix are, which describes, like, they doesn't change? Yes. Sorry, come again. Yes, this is little x. Yes, that belongs to this capital X. Yes, yes. So if I want to describe in the picture, so let's say this. I hope this can actually go. So let's say this is my state space, like right. So this is my state space: x1, x2, and x3. Right. So three-dimensional space. So you have some point here, right? And what you're doing is you are actually taking observables, right? So you're constructing observables. So this is like a function, which is a function of x1, x2, x3, right? So yeah, so that okay, maybe I should do it in two-dimensional, because then it will be easier to draw this. So let's say you have this two-dimensional state space, x1, x2, right? And then you have some point x here, little x, right? So this is my capital X space. Now you construct an observable f. Now this observable f, you can visualize this as x1, x2, and this is your function, initial function f, right? Now just this point x sort of evolves and gives you a new point t of x, right? x1, x2, right? So this is my new point t of x. This is my original point x. Now you want to see, okay, you can also construct another observables, or this. You can ask, just like x evolves to t of x, how this f function will evolve to a new function, right? And that is precisely your kappa of f of x, which is given by f t of x. Okay, so that will be some function. Call it as f1 of x, perhaps, if you want to call it. Okay. So just like you have evolution in the state space on the top, you have an evolution in the of the observable at the bottom. Okay. Okay. So yeah. So going back to this. So if you have a matrix, what's the first thing that comes to your mind? Huh? Eigenvalues, eigenvectors, right? You can ask the same question, because that's the very powerful, right? Because once you have eigenvalues, eigenvectors, you can do diagonalization, you can compute like what are the modes are, what are natural frequencies are, and all those kind of things, right? Now, since we have a linear operator, we can ask the same question. Okay, what are the eigenvalues and eigenfunctions? So instead of eigenvectors, because now we have a operator, eigenvectors becomes eigenfunctions. Okay, so what are the eigenvalues, eigenfunctions? This is very powerful. So I would say that it's not just the linearity of these operators which are actually important. The spectral properties of this operator is actually even more important. Okay? And these are very useful when it comes to control design. Okay? When you want to do control design for nonlinear system, you can actually do control design for nonlinear system based on the spectrum of this linear operator. Okay? I mean, you can do, even for linear systems, finite dimensional linear system, you can actually do control design based on the spectrum. Of course, you don't do that because we use optimization-based methods, LMIs and things. But underneath, if you sort of open them up, you will see that the eigenvalues, eigenvectors are actually sort of are effectively used whenever you're solving either Lyapunov equations or you're solving the Riccati equations. Okay. A spectrum of the Koopman operator. Now, this is where one has to be really careful, okay, but we'll sort of ignore it for a time being, okay, because this is actually, and I'll do some examples to sort of bring that thing out. So spectrum of Koopman, what is the spectrum of Koopman operator? It's basically the eigenvalues, eigenfunctions. So I will say phi of x is, or let's say use notation phi lambda of x is an eigenfunction with eigenvalue lambda of this Koopman operator kappa, if kappa acting on phi lambda of x is equal to, it's like when you have a matrix, eigenvalue, eigenvectors will be AV equals lambda V. This will be lambda times. So you get back the same function. It's just a scaled with the lambda. Okay? The only difference is that instead of vector now, you have a function. Now if you do a finite dimensional, then this vector will become the function will become a vector. Okay? Now these are actually very important. Okay? Now, because this is an infinite dimension, so if you have an n by n matrix, how many eigenvalues, eigenvectors you have? They may be linear dependent or those things, but you have n eigenvalues and n eigenvectors. Now this kappa is infinite dimensional, so it will have infinitely many eigenvalues and infinitely many eigenfunctions. So that's where the challenges are. Now things doesn't stop here. We become more crazier. Like when you have a finite dimensional matrix, the eigenvalues and eigenvectors, they are always discrete, right? But this object could have a spectrum which is continuous, not just point spectrum, to have a continuous spectrum. Okay, I'll tell you an example where that happens. So those are some of the problems I was telling you yesterday. If you're working in this area, what problems you want to touch and what problems you don't want to touch. So some of these things you don't want to touch, like dealing with spectrum, dealing with Koopman operator with continuous spectrums. Like for example, this is still not still an active area of research. If you have a chaotic system, then then the kappa will could have a continuous spectrum. Okay. But since our ultimate goal is actually to do everything from data, there are limits. Like one of the questions you ask, okay, is what is the limits on data, right? So now if when you're dealing with data, you'll always have finite data. You'll never have infinite data, right? And with finite data, you can only construct a finite dimensional operator. If you have our finite dimensional approximation of the infinite dimensional operator. And when you have finite dimensional approximation of infinite dimensional operator, it will always be a finite dimensional matrix. Okay, now if you have finite dimensional matrix, you will only have a finite spectrum, only finite eigenvalues. So this issue of having a continuous spectrum, which is true in the infinite dimensional space, will not be, you will never able to recover that, at least when you're trying to do with data. Okay, because that's the underlying limit. So when you're dealing with data, some of these things actually becomes complicated. How do you recover this infinite spectrum and so on? So we don't want to get there right now. Maybe we'll talk a little bit more about it later on. But this is a definition. Okay, this is the definition of the eigenfunction with eigenvalue lambda. Okay, and the other part is that there are infinitely many of them. And I will tell you then later on is that if anyway, I don't want to spend too much time on that. I think this is a good point to break, because after this I'm going to do some examples of this Koopman operator and so on.